Hello, everybody. Thank you for joining us. We're going to wait a few more minutes just to see if we can get anybody else to join in here. While we wait, I'm going to put up a poll question regarding your familiarity with pump sizing. So I'm going to go ahead and launch this, and then I'm going to go offline, and I'll join back up in a minute. All right, we're going to go ahead and get going. Thanks, everybody, for joining us. I'm going to go ahead and close out the poll and share the results just so that everybody can see sort of where we are right now. We've got a good little split and then some middle of the road people. Looks like a lot of folks have seen it a little bit, have a little bit of familiarity with it, but it's going to be relatively new. So that's excellent. Thanks everybody for your patience. My name is Darren Myers. I'm the Controls and Embedded Systems Manager at Zoeller. And this is going to be Pump Sizing 101. Before we get started, I just want to cover a couple of details. We have a little chat line that if you have any questions during the course of this, you can shoot in the chat. We have somebody monitoring that and we'll get back with you. You'll see there on the screen, there's an email address, webinars@zoeller.com. If you have any questions, after we wrap up today, you can send them to that address, webinars@zoeller.com, and we'll be sure to get back with you. We're going to be, as I mentioned before, actively taking questions during the course of the webinar, and we may review those and go over a few of those questions if we feel like they're valuable to the group there at the end. So now that we've covered the basics, I want to start off by letting you know a little bit about me. My name is Darren Myers. I am currently the Controls and Embedded Systems Manager at Zoeller. I've worked there for about 15 years, but most of my time has been spent in applications. I ran our inside sales department for a little while, and over the course of my time, I've seen a lot of different kinds of pumping applications. And so it's given me a lot of exposure, and I've been able to understand how pumps and piping networks interact with each other. So with that said, we're going to go ahead and jump into the presentation. Pump Sizing 101. When we talk about the types of pumps that Zoeller Pump Company offers, we generally are dealing with wastewater pumps. And so this wastewater comes from a variety of different sources. It could come from groundwater type applications. You know, this is really what Zoeller is known for in a lot of markets. We have sump pumps that would keep basements dry, subterranean places dry. We also have pumps that are designed to operate in sewage applications. And so sewage would be anything that is going to make its way through a toilet trap or from any sinks or lavatories or anything like that. And then third, we often deal with water that we call effluent. And effluent is the liquid that will decant off of a septic tank. So the purpose of a septic tank, sewage comes into one side. And that sewage contains all of the solids, fats, oils, and greases, and paper products, human waste. That water normally spends a couple of days inside that tank as it traverses from one side to the other. And over the course of that time, the liquid separates from the solids. And so what decants off the other side or out of the other side of that septic tank is what we call effluent. Still a wastewater, but it lacks the solids and particulate matter that you would normally see in sewage. So if we're going to choose a pump for a particular application, we have to start with some knowledge about where that water is coming from, because that will help to guide us on that initial step, which is choosing the style of pump. So no surprise, pumps have different characteristics depending upon where we intend to use them. For instance, sump pumps, which are going to be dealing mostly with groundwater, there may be some minimal amount of solids in that water, generally in the form of maybe silt or sand, small rocks, things like that. But we're not going to expect any large solids to pass through those pumps. And so as a result, the applications there, these particular pumps don't handle solid or aren't intended to really handle solids. The other part with these pumps, they can be automatic or non-automatic. And so what we mean by that, if you look at the image there on the screen, there is a little side switch. And that side switch has a float. That float rises up and it will turn that pump on or off automatically. So you can drop that particular pump into a sump pit, you can plug it into the wall, and its operation will be controlled automatically. A non-automatic pump doesn't have that switch and would normally require some kind of an external float switch or control panel to make it function. Either an automatic or a non-automatic pump is appropriate for a sump application. A sewage pump, by comparison, is designed to handle larger solids, generally 2-inch solids or larger. Again, this is to account for anything that might be able to be flushed down a toilet trap. That anything that you flush down a toilet should be able to pass through that pump without causing any clogs or issues. As with a sump pump, these pumps can be either automatic or non-automatic. And lastly, we'll talk about effluent pumps. Effluent pumps are similar to sump pumps in many ways. In fact, they share a lot of the same models. An effluent pump that's pumping the liquid that comes out of a septic tank, that liquid should not have solids, and so the effluent pumps that we have really aren't designed to move larger solids. They would get clogged up easily if you were to put them in a solids-heavy environment. The difference from a sump pump, however, is that we do not want to use an automatic pump in that application. We really want to deal with non-automatic pumps only. The reason for that is an effluent application, the water coming off of a septic tank, has present in that environment corrosive gases. And so if we have a pump, like a sump pump, like the image of the sump pump there, that has a side switch, those corrosive gases, if you allow that water to ride up and down the side of the pump, those corrosive gases can attack that pump and cause damage in the long term. What we want in an effluent application is for that pump to be fully submerged at all times. So we're going to use a different kind of a float switch, one that will shut off high enough where the water still is above the top of that pump. And it will keep the corrosive gases from attacking the seals and even the cast iron itself. So when we go down the road of selecting a pump, the first thing that we want to do is determine what the project needs. For instance, what kind of solids handling capability are we going to need out of that pump? What kind of flow rate do we need out of that pump? So how much water do we need that pump to move? And then where does that water need to go? Is it moving through a short stretch of pipe and just going beyond the wall and doesn't get into the yard? Or is it going to be pumping for several hundred feet to a very high elevation? Those are all going to influence what a project is going to need. So once we have an understanding of the project's requirements, we're going to turn our attention to the pump and make sure that we pick a pump that can sufficiently satisfy those requirements, that it should be able to meet the requirements without vastly overperforming. And if we do that, very likely it'll be an economical choice as well. It's important to understand that there are pumps and there are systems. Pumps are easy to understand. We all can go into a store or a plumbing wholesaler and we can point to a pump on the shelf. We know what it is. It's a physical object, comes in a box or on a skid. We can pick it up, we can hold it, and we can drop it down into an application. The pump is the thing that's moving the water. The system, however, is a different thing entirely. The system is what the pump is going to push water into. Think of the system, all the system is the piping network that attaches to the pump and carries the water from the pump, from the start, to wherever that water is ultimately going to end up, where it's going to leave the pipe system and either flow into, could be flowing into a sewage system, could be flowing into a septic tank, could be flowing into the backyard if it's just a sump water application. So the pump we understand, the system is the piping network and the valves and fittings and everything else that water interacts with after it leaves the pump. So if we consider what a pump does, there is a rotational aspect, a component inside that pump called an impeller, and there's a motor that spins that impeller, and as that impeller moves around, it's adding energy to the water in the form of motion and pressure. So in pump selection or pump sizing, the two most important characteristics that we are going to try to determine and subsequently use are flow or flow rate and total dynamic head. And I'll cover these terms here in the next slide or two. Total dynamic head is also very often abbreviated just as TDH. So flow is something that many of us can understand pretty easily. It's the rate at which water needs to move. We normally talk about flow in pumping applications in terms of gallons per minute, or GPM. Depending upon where you are in the world or what application you're dealing with, you might also use different units for measuring flow rate. Could be liters per hour, could be cubic feet per second. If it's a large wastewater plant, it could be millions of gallons per day, MGD. But for our purposes in selecting these kinds of pumps, generally we're talking about flows in GPM, or gallons per minute. Total dynamic head is a kind of a long and complicated term for pressure. Pretty simple concept, actually. The total dynamic head is a measure of the back pressure that the system applies to the pump. So when a pump kicks on, it tries to push water into a piping network. And the piping network responds by pushing back on the pump. And so the pressure with which that system pushes back is called total dynamic head. So where that phrase comes from is because it's the total dynamic head, because it's the sum of three separate components. We're going to talk mainly about two, but total dynamic head is the sum of static head plus friction head, plus in certain circumstances, more advanced applications, you may have something called operating head. And we're not going to get too deep on that, but I might mention it a time or two in the presentation. Total dynamic head, as I said, is a measure of pressure, but we measure it with a unit of feet of water. And sometimes we'll shorten that just to feet. We'll talk about, this application has 20 feet of total dynamic head. And what we mean is the total dynamic head is equal to 20 feet of water. And it can be a little bit confusing because we don't think about, when we see feet, we think about a length measurement. We don't think about it that feet of water could be a measure of pressure. But if you think about terms that you may have heard in looking at the weather, they often talk about barometric pressure in millimeters of mercury or inches of mercury. And what that's measuring is, it's a very similar kind of a concept. Feet of water, it's measuring the pressure associated with a particular depth. And you could convert that to PSI if you needed to. But the main thing to understand is feet of water is not necessarily a length, it is a measure of pressure. So we have flow and we have total dynamic head. And we need a way to be able to graphically represent that. So if we have a scale that starts at 0 and counts up to some higher value, and we use that scale to plot flow rate. So as the flow rate increases, we're going to move from the left to the right along that scale. And we have another scale that's vertically, and that is a measurement of total dynamic head. Again, starting at 0 down low and counting up as you rise. This provides for us a good mechanism for understanding, for instance, the relationship between flow and head in an application. So what I have on the screen here is a plotted point, and that point represents 20 gallons a minute at 45 feet of total dynamic head. If we had a different point, then we wanted to plot 50 gallons a minute at 15 feet of total dynamic head, it would look like this. Lastly, just to drive the point home, if we had 55 gallons a minute and 35 feet of total dynamic head, we would plot it this way. So when we plot a point on here, it just gives us, it tells us some flow rate and it tells us some associated total dynamic head. And this becomes useful for us in a couple of different ways. All pumps that exist out there have some performance curve. And all pump manufacturers, Zoeller is no exception, we have pump performance curves that are available for all of our pumps. And so what that performance curve does, it shows the relationship that that pump has between flow and total dynamic head. So for instance, I'm showing a fairly typical pump curve there on the screen. And so that performance curve shows you what you can expect out of a pump when you put it out into the world. And this is what I mean by that. If you have that pump and that pump is moving water at a rate of 20 gallons a minute, if we take 20 gallons a minute and we come up to that pump curve and then go across to the left-hand side there, we can expect that that pump can produce a pressure of 26 feet of total dynamic head. when it's driving water forward at 20 gallons a minute. If that pump was instead doing 30 gallons a minute, you can kind of come up and come across there, and you'll see that that pump can produce a pressure of about 15 feet of total dynamic head when it's moving water at a rate of 30 gallons a minute. And as a third point here, just to show you one additional example here, this represents a special case where the pump is actually not moving any water at all. It's producing maximum pressure, but no flow. So in this case, this particular pump associated with this curve can produce, looks like about 31 feet of total dynamic head, maximum. But when it's doing that, it can't move any water. So pump curves can look different ways. Sometimes they're smooth, like the first one that was shown. Sometimes they have a little bend and it may drop vertically down. That little bend there is what we call the knee of the curve. Not all curves have that. It's kind of a special case. But pump curves can, certain pumps can move a lot of water and produce a lot of pressure. Some pumps have lesser performance. They can be shallow, they can be steep. So a pump curve can look a lot of different ways, just depending upon the characteristics of that particular pump that's represented. And the important thing to understand is that a given pump is always going to operate somewhere along that curve, because that curve represents the relationship between flow rate and total dynamic head. What people often don't understand, if you haven't been in this industry very long, is that systems have performance curves too. And again, just as a refresher, when I say system, I'm talking about the piping network. I'm talking about everything that the water flows into and through after it leaves the pump. So that system is all the pipe that you have to buy, all of the fittings, the valves like the check valves and the shutoff valves. So a system also has a performance curve. It looks a little bit different. It has a different shape than a pump curve, but a system curve is sort of a fingerprint for a given piping network. And if you change the characteristics of that piping network, if you make the pipe longer, for instance, or if it climbs and goes to a higher elevation, or if it has more fittings or fewer fittings, the system head curve associated with it will change. The characteristics change. It'll have a different fingerprint. Sometimes system head curves are very shallow and they rise, slowly. Sometimes they're steeper and they might rise more quickly. But they all generally have this typical shape. They're going to start over on the left-hand side against that total dynamic head axis. They're going to start by coming straight off from that axis perpendicularly, and then they're going to rise up. And again, they might rise slowly, they might rise steeply. But where they start on that axis can change. They might start down at the 0 point, or they may start, higher up at some different elevation. The important thing to understand is they all have this shape, and every system has a curve associated with it. Now let's imagine that we have some system out there and that this is the curve that represents that. So, our system, for instance, might pump water up 15 feet into the air, and it might have some length associated with it and some number of fittings. If we take that curve and we superimpose on it a curve associated with a pump, so some pump that we take out of the box and we hook it up to this system and we turn it on, where those two curves interact is very important. That gives us an operating point. Where the pump system or the pump curve interacts with the system curve is called our operating point. And it tells us if we were to put pump 1 into this system, we can expect that we're going to get 40 gallons a minute. If we put pump 2, a separate pump, if we don't put pump 1 in and we instead select a different pump, we're going to get a different interaction with that system. So in this case, if we use pump 2 instead of pump 1, we may only get about 25 gallons a minute. And you can see that if you were to project that operating point straight down, that's where I'm getting that 25. And again, if you look at the intersection between pump 1 and the system head curve, it'll intersect there at about 40 gallons a minute. Being able to understand this graphically gives you a lot of information. Pump curves are available everywhere. If you go to Zoeller's website and you're interested in a particular pump, we have curves for everything that we produce. So if you go to our website and you look up a particular model and you look into the various tabs that we produce, we have pump curves that are associated with those different models of pump. But system head curves are not that way. System head curves are unique to a given project. There isn't a catalog that you can go to find what your system head curve is. We have to calculate that. We're going to have to perform some calculations given the information that we have in order to figure out what our performance needs to be. So why would we even care about system head curves? Some of you have probably had pump sizing classes in the past that you may have taken, and they may not have even mentioned system head curves before. So why would we care about it? And I think it's important to care about it because they're a really nice tool to have. Let's imagine for a minute that we have some pump and we have some system. So our system consists of 80 feet of 1.25 inch pipe. We'll say it's PVC pipe. And that system also has one check valve in it, and it has 6 elbows. We'll say they're 90-degree elbows. And from the point at which that system, that piping network leaves the basin, it's going to rise over an elevation difference of about 10 feet. So that is the system that we have. And if we wanted to know what pressure we need to drive water at 25 gallons a minute through this system, if we had the system head curve, that becomes a very easy question. So if we could snap our fingers and have a system head curve, and this was the curve that was associated with that piping network, that 80 feet of 1.25 inch pipe with a check valve and some elbows rising over an elevation of 10 feet. If this were the system head curve, we would simply find 25 gallons a minute, project that up to the curve and come across. And so it would tell us that we would need a total dynamic head, that the system is going to push back. If we try to push 25 gallons a minute worth of water into that piping network, the network's going to push back on that pump with 20 feet of total dynamic head. That's why it's valuable. If you have it, it becomes really easy. If you needed to know what the flow rate was at 20, again, you would just project 20 up to the curve and across, and it would maybe be closer to 15 feet of total dynamic head. Of course, we don't often have a system head curve. And so if we don't have a system head curve, we have to go through the traditional steps of pump selection and pump sizing. If we want to do that, the first step is to pick an appropriate flow rate. And there are different methods depending upon the application, but it all starts with the flow rate. Once we have a flow rate, we're going to figure out what our total dynamic head is. We're going to run some calculations. And we need to identify the static head and calculate the friction head. And we'll talk about these terms because they may be unfamiliar to some of you. As I mentioned, it all starts with the flow rate. The flow rate is essential to start with because calculating total dynamic head depends on the flow rate. If the flow rate changes, the total dynamic head will change as a result. So the general steps are this. We're going to identify the system characteristics. So that means knowing what your pipe size is, knowing how much pipe length you have, knowing what elevation you overcome, knowing what fittings you have. So identify all of those system characteristics. And then we're going to pick a flow rate, and we'll use that flow rate along with the system characteristics to compute the total dynamic head. And once we have flow and total dynamic head, those 2 points together, if we plot those on a graph like what I was showing earlier, that gives us a design point from which we'll pick a pump. Now it all starts with the flow rate. And so it's important to know how to find a flow rate. Ideally, for a lot of applications, the flow rate might be provided to you. It may exist on a set of plans or in a set of specifications. And so you just have to identify what it is. It's not a matter of calculating it. It's just a matter of putting your finger on what has already been calculated for you. And there are different methods that exist for computing flow rates. And I'm not going to get into that deeply, but things like the Fixture Unit Method might be familiar to some of you. That is a method for determining a flow rate, often in like sewage type applications. But just as some rules of thumb, if you have a residential application that you're trying to evacuate water, let's say out of a sump pit in the basement, if it's a residential size house, a normal size house, not a gigantic mansion, but in that application, if you had a clay soil, then you're probably looking at a sump pump flow rate necessary in the range of 20 to 25 gallons a minute. If instead of clay soil, you had sandy soil, that flow rate would go up. maybe to 40 or 45 gallons a minute. These again are just rules of thumb. The reason that it goes up is if you have sandy soil around that property, water moves far more easily through sand than it does through clay. And so it can travel more rapidly. If it's raining hard outside, that water can move through the sand and get to your sump basin much more quickly. So you may have to have a higher flow rate in your sump basin to keep up. If you have an effluent application in a residential type of situation, and that effluent is being pumped out to a gravity drain field, you're probably looking at 20 to 40 gallons a minute as a flow rate range. If you have a sewage basin in a residential application, you're looking at maybe 25 to 40 gallons a minute. These are, again, just some rules of thumb, some starting points, and there are different ways of calculating if you do not know it. So total dynamic head has multiple components to it, as I mentioned earlier. The two primary ones that you're almost always going to see are static head and friction head. And in certain applications, as I mentioned, there may be a third component called operating head. Operating head might exist if you need to, let's say, run a sprinkler, or if you need to run a low pressure pipe network for distributing effluent. And I'm not going to get into that. I just wanted to let you know that it exists. The vast majority of pumping applications, if it's going to be a sump or a sewage pump, they're generally not going to have operating head. They're going to just have static head and friction head. Static head is the first of those two components, and it's a very easy thing to understand. Static head is really just the elevation change from the water level in your basin up to where the water leaves the pipe. So we have a little image on the screen there. In that application, if the elevation difference between the water level and where your water leaves the pipe is 10 feet, 10 feet is going to be your static head. It's important to note that the amount of pipe that you have doesn't really matter to static head. You might have hundreds of feet of pipe, but the only thing that matters is the elevation difference between where you're starting and where you're finishing. That is what static head is. So in this case, the static head is equal to the elevation change, which is 10 feet. The next step that we have is to calculate the friction head. So let's talk about what friction head is. So friction is a measure of the resistance that the water has as it moves through the pipe and the fittings. And you can think about it this way. I guess first, the longer the pipe that you have, the greater the friction head. So when we were talking about static head, it didn't matter how long of a pipe you had. The only thing that mattered was the elevation difference. But when it comes to friction head, the more pipe that water has to interact with, the more frictional losses or frictional resistance will build up. Also, the faster you try to shove water through that pipe, the more friction head you're going to see. So friction head depends on a couple of different things. It depends on your pipe size, the pipe length, how much flow you're pushing through it. All of those things matter. And so you can imagine, if, to draw an analogy here, let's say that you're driving in your car and you're in a subdivision. And so there are kids present and you're driving at a nice safe rate of speed. You're probably going maybe 15 miles per hour. It's a nice day. You roll down the windows and you stick your hand out of the window as you're driving at a nice leisurely pace. And you feel the breeze on your hand. There's some resistance on your hand, but it's not a lot. You don't feel a whole lot of pressure pushing against your hand. But as you increase your speed, and let's say that you're driving down a highway now and going at highway speeds, if you were to stick your hand out going 60, 70, 80 miles an hour, it's going to be a different story. You're going to feel a lot more pressure, just like this guy's feeling. So again, the amount of pressure that you see in a pipe is related to the flow rate in the pipe. So in this case, the greater the flow rate, the greater the speed, and that's kind of like driving at a faster speed in your car. So there are factors that affect the friction head. As I mentioned, the flow rate affects it. Also, the characteristics of your piping network. So things like the number of fittings that you have and the size of those fittings and what kind of fittings they are. The overall length of the pipe, the diameter of the pipe. These are all factors that have an effect on calculating friction head. So when we start down the road of calculating this stuff, we're going to start with the fittings. And I wanted to point out that along with this webinar, there are a couple of documents that you can download. One is a friction loss chart. And this chart here that is associated with fittings is located on page 2 of that document. The other file that's there for you to download is an overview of pump sizing in its entirety. So after we go through this in detail, if you want something to just kind of remind you of the steps, that's what that other document is. It's a Word document. You can download it and print it out, and it provides sort of a brief but sufficient step-by-step account of how to do pump selection. So this is an equivalent fittings chart. And the way that you read this, over on the left-hand side, there are a number of different kinds of fittings. We have different kinds of elbows, T's, there's a check valve, there's a gate valve or a shut-off type valve. And along the upper edge, there are different pipe sizes. And so the way that you read this, for a given fitting, there is a value in the chart that we'll find. So for instance, if we have, let's say that we've got a check valve that's 1 1/4 inches. If we come down from 1 1/4 inches and we come over from a check valve, we're going to find a value of 11.5. And what that value is, what it's saying is that there is enough friction loss in a single check valve to be equivalent to 11.5 feet of straight pipe. So the next step we're going to do is compute the friction loss in all of the piping that we have. But step 1 is to look at all of our fittings and come up with their equivalent lengths of straight pipe. As another example, while we're on this page, if we had a 90-degree elbow, 1 1/4 inch 90-degree elbow, you can see from the chart there that the value is 3.5. So that means that one 90-degree elbow has enough friction to be equivalent to 3.5 feet of additional straight pipe in your application. So the other part of that document that you can download is this friction loss chart. And friction loss charts come in a lot of different shapes and sizes, and they contain different kinds of information. This is a particularly handy one, I think. And you can see over on the left-hand side, there are values for gallons per minute. So as your flow rate increases, down along the left-hand side there, the values in the chart will also increase. Along the top, as before, there are different pipe sizes. So underneath each of these pipe sizes, this particular chart has 2 columns. It has a velocity column and it has a loss column. We're more interested right now in the friction loss, or that loss column. So if we had an application where we wanted to find what the friction loss was, if we were moving 25 gallons a minute through an 1 1/4 inch pipe, this is how we would do it. 25 gallons a minute over on the left-hand side, we find that and then we come across. Then we look for 1 1/4 inch pipe, find the loss column and come down. And where those two intersect gives us the friction loss value. In this case, it's 7.89. Now, what is that 7.89? Well, up at the top of the chart, it tells us 7.89 in this case, that is the friction loss or the friction head. And the units are feet of water, so that's consistent with what we've been talking about. And specifically, it's the friction loss through 100 feet of pipe. So stated another way, if we had 100 feet of 1 1/4 inch pipe and we pushed water at 25 gallons a minute through that pipe, we would have a friction loss or a frictional resistance of 7.89. These friction loss charts are set up based upon the kind of pipe that you're dealing with. And this particular chart is set up for Schedule 40 PVC pipe. There may be different friction loss charts for cast iron pipe or even Schedule 80 PVC pipe. And you can find all of these online, but there are other friction loss charts available out in the world, and you can do a Google search and find plenty of them. So if we look at an example here, and we wanted to know what's the friction loss for this system, the system being 80 feet of 1 1/4 inch plastic pipe with 1 check valve and 6 elbows. If we wanted to know what's the friction loss factor if we push water at 25 gallons a minute through this system. So from the fittings chart that we were just looking at, we'll start with the fittings. We said here in this little example that we've got one check valve and 6 elbows. So in the fittings chart, we find those categories. There's a 90-degree elbow and there's a check valve. And then all of the piping that we're dealing with here is 1.25 inches. So we find the 1.25 inch column. And we can see that one check valve has an equivalent length of 11.5. It's like having 11.5 feet of extra pipe in our system. Each of the elbows has an equivalent length of 3.5, but we have 6 elbows total. So we do the multiplication. 6 times 3.5 is equal to 21 feet. So those 6 elbows is like having 21 extra feet of pipe in our system. So then we would add those up. Instead of doing our friction loss calculations based on 80 feet, we're instead going to take 80 feet plus an additional 11.5 feet plus an additional 21 feet, and we're going to do our calculation on 112.5. So even though we only have, in reality, 80 feet of pipe out in the field, the fittings add some additional friction loss, and it's like having another 11.5 plus 21 feet added onto it. So 112.5 feet is what we're going to base our calculations on. So then from the friction loss chart, we want to know what the friction loss is at 25 gallons per minute. So we find 25 there on the left-hand side. We find our 1.25 inch pipe, and in the loss column, we come down. So we find from the chart that the value is 7.89 feet of loss for every 100 feet of pipe that we push 25 gallons a minute through. So some examples of this. Let's say that we wanted to know how much loss we had in that same pipe at 25 gallons a minute. But let's say instead of 100 feet of pipe, let's say that we only had 50 feet of pipe. Well, in that case, you would take that 7.89, that value that you pulled from the chart, and you would divide it by 2, because again, the chart is set up for pipe lengths of 100 feet. So if we only had half that, you would divide that value by 2. By comparison, let's say that you had 200 feet of pipe. Well, if you have 200 feet of pipe, you're going to have twice the friction loss. So you would take that value out of the chart, 7.89, you would multiply it times 2 to get a different value. So in general, the formula looks like this. You'll have your loss factor from your chart, you'll divide it by 100, and you'll multiply it times your total pipe length, and that's your pipe length plus your equivalent length of fitting. So in this case, 112.5. So taking all of those values, we had 7.89 was the value that we pulled from the chart. That's 25 gallons a minute and 1.25 inch pipe. That's the loss. We'll take that 7.89, divide it by 100, and then we'll multiply it times 112.5, and that gives us a friction loss of 8.9 feet, which we would generally probably just round up to 9 feet. So then we add everything up. Our total dynamic head is equal to the static head plus the friction head, and now we know both of those values. The static head was the elevation difference from a few slides ago, and it was 10 feet. We just calculated our friction head. It was 8.9 feet. That was calculated from the fittings chart and the friction loss charts. So we add them up. Total dynamic head is equal to the static head plus the friction head. And in this case, that adds up to 18.9 feet. So flow and total dynamic head together give us a design point. Those 2 points, now we have flow rate, which is 25 gallons a minute. We have total dynamic head, which is 18.9. So as you might imagine, we're going to go to one of those charts that we were looking at before, and we're going to plot that point. So we find 25 gallons a minute on the lower axis, and we find 18.9 on the vertical axis, and then we find where those 2 points intersect. And that's going to be our design point. So now that we have a design point, we want to pick a pump that can meet that design point, that can meet that performance. So let's imagine then that we have 3 pumps that we're going to consider. That is the design point that we need. We need a pump that's going to do at least 25 gallons a minute against a pressure of 19 feet. So these 3 pumps are ones we're considering, but only a pump that can pass above or to the right of that design point will be sufficient. So the red curve that you see on your screen passes below the design point. It is not sufficient to meet that design point. It can't do the performance that we need it to do. And so we're going to take that out of the picture and not consider it. So generally, the pump that is closest to your design point is often the one that's going to be the most appropriate. And that's not always the case, but it's a pretty darn good rule of thumb. And in a situation like what we're seeing here, these two pumps, I would very likely just pick the pump that is the closest. And it's important to remember, in this case, we are looking at a design point on the screen. And that design point is associated with our system, that piping network. And it's good to remember or know that even though we don't know right now what the system head curve looks like, if you recall us talking about the system head curves, we don't know what it looks like, but it exists. The system that we're talking about has a system head curve. It has a fingerprint. And if we knew what it was, that would give us some additional information. So here is the bonus tip. First off, the design point that we came up with, that 25 gallons a minute at 19 feet of total dynamic head, that is a point on that system head curve. The other thing to understand is that the system head curve is going to start at the elevation of the static head. And in this application, our static head was 10 feet. So that's where that curve is going to start. And with just those two pieces of information, you can kind of eyeball in what your system head curve is going to look like. Again, it's going to come off of that vertical axis perpendicular, and it's going to swing up and it's going to arc through the design point. And then it will continue traveling in that shape. It'll travel out and up. And if we envision that, we can take the intersection points of where those two pumps intersect with that system head curve, and that will give us a really good idea of what those pumps will actually do when we put them out into this system. So we needed a pump that would do 25 gallons a minute against a pressure of 19 feet total dynamic head. If we use that orange pump curve, we're going to overperform that just a little bit. We're going to probably get maybe 26 or 27 gallons a minute out of that pump. But if we were to use that other pump, the purple curve, it's going to produce maybe 32 or 33 gallons per minute. So if we only need 25 gallons a minute out of the pump, why put the larger pump in there? It's probably going to cost us more, and it's going to give us more performance than we really need. So in this case, the orange pump would be the best choice. So now, with our remaining time, we're going to look at a real-world example and go through all of these steps. We're going to imagine that we have a small office building that's going in, and they come to us. They're either building or redeveloping this, and they're looking for a sewage pump because they're going to put a little sewage basin down in the basement to collect the sewage, and they're going to pump it up to a gravity sewer system that's located near the street. And the required flow rate that they've told us for this application is going to be 40 gallons a minute. So the first thing that we need to know is, what is the elevation difference? How far up from where that basin is going to be located to where the water is going to exit that pipe? What is the elevation difference between those two? And that's going to tell us the static head. So if we consult the plans, we're going to see that for this particular job, the elevation difference between where our pump is located in the basement to where we're going to be dumping that water into a manhole at the street is going to require a rise of about 15 feet. Now we're going to have more pipe than that, but the elevation difference is just 15 feet, and that's our static head. The next piece of information that we need to know is, what is our piping going to look like? We need to know how much pipe we actually have. We want to know what pipe diameter we're going to be dealing with and what materials we're going to be dealing with, and we need to know what fittings are going to be required. So if we check the plans, we see that to get from where the basin is located up to where the manhole is located at the street, it's going to require 150 feet of pipe. And we can also see that the pipe diameter is 2-inch, and that Schedule 40 PVC is going to be appropriate for this job. So that's what we're going to use. The fittings that will be required to get us from inside the building out to the street, we're going to be using a check valve, 4 90-degree elbows, 2 45-degree elbows, and a gate valve. So we want to take a look at that fittings chart. We have a collection of fittings and we need to see how much straight pipe is that equivalent to. So in reality on this job, we have 150 feet of 2-inch pipe. That's the literal amount of pipe that we have that's running out there, but we need to consider how much extra pipe we're going to need to consider in order to account for the extra loss in the fitting. So going back to our friction loss chart, and on the back page of that friction loss chart, or the second page, is this equivalent fittings table. And so for each of the fittings that we have, a 2-inch check valve, the elbows, the shutoff valve that we have, we pull those values from this table. So we can see that that 2-inch check valve has a value of 17.2, meaning that one 2-inch check valve is equivalent to having an additional 17.2 feet of straight pipe. So we do that for all of our fittings, and we consider how many fittings we have, and we do a multiplication across. So you can see all of those values there on the top right. And if we add them all up, it will tell us we need to consider an additional 45 feet of piping beyond what we actually have in the field. There's 150 feet of pipe that we actually have, but we're going to add to that another 45 feet to account for the friction loss in the fittings. Once we know that, we can go to our friction loss chart. We know that the material that we're dealing with is Schedule 40 PVC pipe. So we want to make sure that the friction loss chart that we're looking at is set up for that, and in this case it is. We were told early on in the job that we needed 40 gallons a minute. That was the design flow that we had to have. So we find 40 gallons a minute over on the left-hand side. The pipe is 2-inch, so we find that loss column under the 2-inch pipe, and we find out where those values intersect. We find that the friction loss value from the chart is 2.64. So that's our friction factor, 2.64. So summing up what we know here, the actual pipe length is 150 feet, but the fittings act like another 45 feet. So we're going to add those two values together, 150 feet plus 45. We have a friction loss factor of 2.64, and that 2.64 feet of loss accumulates for every 100 feet of pipe that we go through. So going back to that general formula, we're going to take the loss factor, divide it by 100, and multiply it times the total pipe length that we need, which is going to be 195 feet. And that's going to give us the friction head. So 2.64 is our loss factor. Divide it by 100. Multiply it times that 195 feet. And what we find is that we have a friction loss in this application of 5.2 feet. That gives us now our design point. We know that the flow rate is 40 gallons a minute. Our total dynamic head is going to be the sum of the static head plus the friction head. And the static head is 15 feet. The friction head is 5.2, which means that our total dynamic head is the sum of those, or 20.2 feet of total dynamic head. That's our design point, 40 gallons a minute at 20 feet of total dynamic head. If we then take that value and we go to a family of pump curves, this is a family of sewage pumps because part of the requirements of this job, they were going to put in a sewage pump. So we're looking at a family of sewage pump curves, and we're going to plot that point. And you can see there, 40 gallons a minute against about 20 to 21 feet of total dynamic head. We plot that point, and then we're going to pick a pump curve that exists above that. That's going to be sufficient to meet that condition. And in this case, that Model 270 looks like a pretty good choice. So that is how you do it by hand. That's how you work through the numbers, work through the calculations. Again, I would encourage you to check out that little cheat sheet that I've got in the documents section. And going through it by hand, those are the steps that are involved. It's good to know, though, that there are pump sizing tools that are available. If you go to Zoeller's website, go to zoellerpumps.com and go to the Sizing Tools tab, you'll be able to log in to the pump sizing program. If it's your first time going, it'll ask you for some information and to create a little account. We do that because you can save sizings within there. If you have a project, you can put in your information. It will save that information and you can revisit it later. But the sizing tools are very intuitive. When you go to this program and you launch it for the first time, it asks you a series of questions about what you know and what you don't know. Do you know what your flow rate is? Do you know what your total dynamic head is? If you don't know those, it will help you to figure them out. So it sort of takes you step by step through those processes, and it will ultimately guide you to a design point and recommend typically 3 pumps for you to choose from. So with that, we have reached the end of the presentation today. It's going to conclude our webinar. If you have any questions for after the webinar, please send those to webinars@zoeller.com. We're going to check the chat information that's been happening, and with the few minutes remaining, we may see, do we have any questions that we want to go over here? One question is, does Zoeller publish system curves for all pumps? And so one little terminology issue with that, based on the presentation that we've had today, we've got pump curves and we have system curves. So when I hear system curves, I'm thinking about the network associated with the piping. So just a little note about that. But Zoeller does publish pump curves for our products. There may be a few products like some utility pumps where there may not be a curve that's published or curve available. It may rather instead give some values, like it'll give you some flow values and it'll give you some associated TDH values, or it might tell you like how many gallons per hour that pump would send out into the world, at different pressure points. For utility pumps, we wouldn't really put a utility pump in these kinds of applications. Any of the pumps that you're going to need to do a sizing for, or that you would be selecting in a pump sizing application, we're going to have a pump curve for. So you would be able to find it on our website. If you're having difficulty finding it, please give us a call. We'll be happy to help you out to find that. The other question had to do with temperature. And somebody asked, I have been told in the past, the temperature of the fluid can affect the friction losses. Do we compensate for temperature when we're sizing a pump for a system? It's a great question. And the answer to the first part, you're correct that as temperature changes within a fluid, its viscosity can change a little bit and the friction losses can change a little bit. The good news in dealing with water is, even though those changes may occur, they're pretty minimal. And it's generally not anything that you would need to account for. If you're dealing in certain applications, let's say, you're dealing with water that's a very high temperature, or there may be some other concerns that we might have. In general, I think for wastewater type applications, being concerned with the temperature of the water really is a non-issue. Again, it would be in certain industrial applications. If you were pumping a more viscous fluid, let's say we're pumping maple syrup, it's going to be very, very different if you're pumping maple syrup that's warm or you're pumping maple syrup that's very cold. The fluid properties change considerably. Water is a lot easier to deal with. Water just before freezing doesn't have much different property than water that's just before boiling. So that's pretty good. All right. The next question that we'll talk about here, when calculating friction loss for a system with multiple pipe sizes, do you just use the average pipe size? And I would say it could actually be tricky to try to do that, because let's say that you had 2 pipe sizes that were 1.5" and 2". You're not going to find a friction loss chart probably for an 1 3/4" pipe. That doesn't exist. So that wouldn't be the way that we would tackle it. What you would do in a situation, if you have 2 different pipe sizes, from a friction loss standpoint, you would treat those 2 pipes differently. So you would do a friction loss calculation for the first pipe that is a certain size. So you would count the fittings of that size, the total length of pipe that you have. You would convert those particular fittings to some additional pipe length and do your friction loss calculation for, let's say, the 2" pipe. And then you would do a separate friction loss calculation for the 1.5" pipe. So you would add up those fittings and convert those to an equivalent length. So you would end up with 2 different friction loss values that you would then add up. Again, friction loss is cumulative. So as you go through one pipe, you're going to have a certain amount of friction loss. But when you go through a different characteristic pipe, you're going to have more friction loss, and you would just add those 2 together. So you would treat them as though they're 2 different pipes, get 2 different friction loss values, and then add them together. All right, a couple of other questions that have popped up that I think might be valuable for people. There was a question, what if you cannot obtain the GPM from the contractor or the engineer. How does this change the approach? So I could probably do actually an entire other webinar for determining what the flow rate is. And unfortunately, we don't really have the time for that here today. So I tried to give some rules of thumb, but there are various methods that exist. For the time being, I would say if you have an application and you're curious about it, or you're at a loss as to what flow rate to use, give us a call. We're happy to help you out. We're happy to look at your issue and see. The other thing that I would advise you to do is to check out our pump sizing application online, because there is a portion of that guides you through that very thing. If you don't know a flow rate, it will ask you some additional questions. It'll ask you about what the application is. Is it a sump pump application? Is it a sewage pump application? Is it an effluent application? And it will continue to ask you questions and guide you into an appropriate flow rate. So if you don't know off the bat, that would be a good place to turn. There was a question about, does this pump sizing method only apply toward sump pumps? And I would say this is going to be applicable for sump pumps, for sewage pumps. Most centrifugal pumps are going to behave this way. Now, when you get into potable water applications with pressure boosters and well pumps and things like that, there could be some different considerations. But for the product line that Zoeller has, Zoeller Pump Company, we again produce pumps that are mainly used for various kinds of wastewater. This is going to be applicable to you. There was a question about control panels. If you're using a Zoeller pump, must you use a Zoeller control panel? It kind of depends on the pump that you're dealing with. The answer is no, you don't have to use a Zoeller control panel. The more sophisticated pumps that we offer, when you get up into some of our more expensive line, we would encourage you to use ours because we have features in our control panel that make use of features in the pump. But generally speaking, control panels, depending upon the application, can often have a very simple function, and you would not necessarily use ours or have to use ours. There was a question about different kinds of 90s. If you have a short turn 90 versus like a long sweep 90, are there differences in friction loss? And this actually will bring up a point that I should have made earlier in the presentation, but the methods of pump sizing that we talked about here, these are all estimations. And it can be easy to get caught up in the decimal points. We see a friction loss factor of 2.64, and it seems very accurate. But all of these are just methods for estimating what friction loss you're going to see and what you're going to get out of your application. So the question about, is there going to be a different friction loss factor for a sweep versus a tight 90? Yeah, there would be different values. Another question that wasn't asked but could have been, if you look at that fittings chart, there's a gate valve, but there's not a ball valve. Is there going to be a different value between a gate valve and a ball valve? And the answer is, yeah, there probably is. But practically speaking, if you see a 90-degree elbow and you use the value out of that chart, whether it's a sweep or a tight, in a very fine detail, it would change your result, but practically speaking, it won't. It might move it, a few tenths. And so is it going to change the pump that you end up selecting? It probably isn't. So even though you may not see fittings that are exactly what you have, very likely if you use the fittings that you see there in the chart, and if you have a shutoff valve, use the value that they have there for a gate valve, and it will cover you for it. And if you have a 90-degree elbow, whether it's a sweep or a tight, just use the value that's there. It'll be just fine. It won't throw your results off in any meaningful way. All right, I think that concludes it. We had some really good questions. There may be some other questions that we will continue to answer offline. Very much appreciate everybody's attention. We're going to go ahead and conclude. Again, if any questions come up after this, please feel free to shoot us an email at webinars@zoeller.com, and we will do our best to get back with everybody through that. With that, thank you very much for joining us, and have a great day.